So, last talk of the day. So I'm going to be presenting some results from my doctoral research project. The goal of my project is to identify ways to improve the efficiency of data assimilation for weather forecasting by lowering the numerical precision of the underlying computations. So I hope to demonstrate that the level of uncertainty we have about data assimilation provides a tolerance within which we can lower precision without incurring unacceptably large rounding errors. And since lower precision computations are faster, this makes data assimilation more efficient. So this is work that I carried out with my supervisors, Peter Dubin, who's now at ECNWF, and Tim Palmer at Oxford. So to begin with, I just want to clarify what I mean by numerical precision. I'm talking about the choice between double, single, and half precision floating point numbers. So this is how we represent real numbers on computers. As defined by the IEEE, double precision, floating point numbers have three different components: the sign, the significand, and the exponent. So you can see they're basically stored using scientific notation. And this shows how the bits are allocated to each one of these components. So for example, double precision floating point numbers have 52 significand bits. And the significand basically determines the leading digits of the number. And that's where most of the bits are allocated. So if we want to reduce precision, that's a good place to start. Typically, hardware only supports single or double precision, but lately hardware vendors are beginning to offer half precision compatible chips as well. The demand for these chips comes mostly from the deep learning community. So when you're training a statistical model, often the quantity of data is more important than the quality. So if you use half precision, then you can increase the throughput of data, training your model, and therefore train a better model. So here's a couple of examples. This one is the Intel Knights Mill Xeon Phi coprocessor, and this one's a NVIDIA GPU. Unfortunately, both of these are well outside of the budget range of a PhD student, but there are ways around it, so we can still investigate half precision by using software emulation. The availability of this hardware and the realization that Moore's law is sort of beginning to decline has prompted people in the geophysical modeling communities to ask just how much precision do we need for our models? And if we want to reduce the energy consumption of our models, could we reduce precision instead of, say, the resolution? So if you look at this table shows the relative energy demand and the forecast error computed from an intermediate complexity general circulation model called IGCM for different setups of resolution and precision. So if you go from 235 kilometers to 315, you lower the energy demand, but you also increase the forecast error. However, you can keep the same resolution and also lower energy demand by reducing the number of bits you use to compute the model. And this has no increase in the forecast error. So the idea of reducing precision is also beginning to catch on in operational centers. So this plot shows the forecast skill of ECNWF's global forecasting system in the northern extratropics for single precision and double precision. And you can see the lines are basically on top of each other. So there's no increase in the forecast error, yet the single precision model is about 40% more efficient. So this brings me to my own research. So just like weather and climate modeling, data assimilation has several sources of uncertainty. The obvious one would be the observation error. So the observations have error, and they're also sometimes quite sparse. The forecast model, of course, is only an approximation to the real atmospheric flow. And also, so for global data assimilation, we don't tend to update that often, so typically 6 hours or 12 hours. And this limits how low the analysis error gets. So given these, how could we reduce precision in data assimilation? And could we, for example, run data assimilation at half precision? And if we can, how could we reinvest any computational resources that we save? Could we run a larger ensemble size, for example? So this is sort of my thesis, if you like, that weather forecasts can be improved for no extra cost by running data assimilation at a lower precision with a larger ensemble size. And so I'd like to describe how this trade-off could work now through a toy model. So instead of starting with an atmospheric model, I'm going to use the Lorenz 96 model, specifically a 3-layer variant of Lorenz 96. So it's like the regular 1-layer Lorenz 96, but it has 3 coupled layers with different numbers of variables. So it's sort of analogous to the real atmosphere. The first is kind of like synoptic scale motion. The second is like mesoscale, and the third is kind of like convective scale motion. Observations of this nature model are assimilated into a forecasting model, which is simplified. So it has a parameterized convective scale. And in fact, I use a stochastic scheme for that. And by mapping the error doubling time of this model with an atmospheric model, we can come up with a time scale to estimate the kind of savings we should expect in weather forecasts. So 10 time steps of the model is roughly 6 hours. Yeah, so just a couple of details about the data simulation. I use the ensemble square root filter devised by Whittaker and Havel. So it's like the ensemble Kalman filter, but it doesn't require perturbed observations. I'm sure most of you are familiar with it. I process observations serially, which means I don't have to do any dodgy matrix inversions. And I take observations every 6 hours. Of course, you should take this comparison with a pinch of salt, because it's actually quite difficult to estimate error doubling times for a model like the 3-layer Lorenz model. And yeah, I use a simple multiplicative covariance inflation applied to the background perturbation matrix and Gaspari-Cohen localization. Now, as I said, we don't yet have access to half-precision hardware, but we can still investigate half-precision by using software emulation. So we developed a Fortran module, which we've called RPE, and you can access it on GitHub here. And this allows us to kind of predict how the model should behave when you use half-precision. This is very briefly how it works. You choose how many bits you want to keep, and all of the bits after that are set to 0, so they have no effect on the value. And there's also, I won't go into detail, but there's also a similar way to reduce precision in the exponent as well. So the first result I'd like to show is the average analysis error as a function of precision and ensemble size. So each one of these points was generated from 10 long assimilation cycles, and the error bars come from the standard deviation. So the take-home point is that there is no change in analysis error when going from double to half precision. It's just 3 flat lines, basically. Now, with a few assumptions, we can estimate the cost of each one of these 9 assimilation setups. Well, the main assumption we make is that the cost of double precision computations is 4 times the cost of half precision computations. Whether this is true or not will actually, it will depend quite a lot on your actual implementation, your actual computational architecture. But we found it's a pretty good rule of thumb. And also our system happens to scale linearly with ensemble size. So this means that double precision with 40 members costs roughly the same as single precision with 80 members and half precision with 160 members. However, the single precision with 80 members has a 30% lower error than double precision with 40, and half precision with 160 members has a 50% lower error than double precision with 40. So this reduction in the analysis error translates into improved forecasting skill. So this plot shows the root mean squared error over time. So this is over about 10 days. So yeah, I initialized forecast from the 3 different simulation scenarios I just mentioned. And this was done over, I think, 500 forecasts on average. So the forecasts are improved when you use half precision assimilation with a larger ensemble size. Similarly, this shows the skill of ensemble forecasts measured by the ranked probability skill score. I won't go into detail about how is this constructed, but basically high is good, low is bad. And actually, in this case, using a larger ensemble size at half precision delivers a day of extra forecasting skill. Now, not all assimilation regimes are tolerant to half precision. So if we reduce the length of the forecasting window from 6 hours to roughly 30 minutes, I call this rapid assimilation, half precision is much worse. So we've kind of lowered the level of uncertainty we have because we're constantly updating, and therefore we need precision more. In fact, even with 160 members, half precision is worse than single with only 40 members. Now, the degradation at half precision is mostly just due to one operation. That's the Kalman filter update equation. So when we're performing rapid assimilation, the background is already very close to the analysis, which means that the analysis increments are very small, and I've written them in a smaller font to represent that. Now, if an analysis increment is too small, it will be rounded to 0 because half precision numbers have a very low resolution. So if you look at this histogram here, I've divided the analysis increments into those that are resolved and those that are incorrectly resolved because of the low resolution of half precision numbers. And in fact, 40% of the analysis increments aren't represented correctly. So that means that 40% of the time, observations will have absolutely no effect on the analysis, and that's why the analysis error goes up. The solution is to keep the ensemble mean of the analysis and background in double precision when performing this computation. And this is actually very cheap, so I'm still doing the forecast model, which is the most expensive part, at half precision. When I do this, I can resolve all of the analysis increments. So going back to the previous plot, this was it without the correction, and this is it with the correction. You don't reduce the error entirely. Half precision is still slightly worse, but it's mostly eliminated. So just to conclude the toy model results before I move on. So lowering precision saves computational resources because lower precision arithmetic is faster. These resources can be reinvested into the ensemble size, thereby lowering the analysis error, which delivers improved forecasts. Not all assimilation scenarios are tolerant to reducing precision, so specifically the rapid assimilation regime is worse at half precision. But we can recover the performance gains from half precision by performing just one operation at double precision. And yeah, I'll be publishing these soon, hopefully. So next, I'm basically going to be performing the same investigation, but with an actual general circulation model. So for that, I've chosen Speedy. For those who aren't familiar with it, it's a simple spectral model you can run on your desktop. It's T30, which means it's roughly 400-kilometer grid spacing, and it's got a fair amount of model complexity. Now, I don't have any data simulation results to show yet, but what I can show is the model itself running at reduced precision. So on this animation, this shows the temperature at 850 hectopascals after 1 month of spin up from rest. And in the bottom right is the number of bits, the number of significand bits that I used to compute the model evolution. And when I press go, I'm going to fairly quickly lower the number of bits I used to update the model down to 10 bits, and then I'm going to keep it at 10 bits for a couple of months so you can see how the model behaves. So let's try that. So I'm lowering precision every 3 days, and then I'm going to keep it at 10. And I think it's quite interesting because you can see that there's definitely some errors creeping in at the equator, but the mid-latitude flow doesn't really appear to be affected, despite the fact that this is a massive reduction in precision. So double precision, remember, has 52 significant bits. And here we're computing it with only 10. So yeah, you can't really tell more without doing a rigorous kind of verification of the climatology of this model. But I think it's very encouraging, and yeah, I'm looking forward to plugging this into an ensemble Kalman filter and seeing how the rounding errors interact with the other errors in the system, like the observation errors and the model errors. So I think I'll leave it at that and take any questions if there are any. So thank you very much.